Nuclear structure. Protons and neutrons are called nucleons. Right here, nucleons. Originally, they were thought to be fundamental, and by fundamental we mean indivisible. They can't be broken apart, there is nothing smaller. However, later in the 20th century, they were found to be comprised of 3 quarks each. Now, don't worry about the quarks, I'm just putting this out there for interest's sake. This is much higher level physics than we're going to do in high school, but there are 6 types of quarks and they have different properties. The proton is made up of 2 up quarks and 1 down quark. The neutron is made up of 1 up quark and 2 down quarks. Again, the reason we're showing this is just so when you hear the term in the future you'll know what it is. But this accounts for the slight difference in mass between the proton and the neutron. You can see where 2 decimal places are the same mass, but the neutron is slightly heavier. Also, the proton has a positive charge and the neutron has 0 charge. The number of protons in a nucleus is called the atomic number and is designated by the letter Z. So that's the atomic number, tells you how many protons you have. The number of nucleons, and recall from the previous slide that nucleons is the total number of neutrons plus protons, and that's the atomic mass number, and that's shown by the letter A. So to find how many neutrons you have, you subtract the number of protons, Z, from the atomic mass, A, and you get this N. So N is A minus Z. To specify a nuclide, which is a fancy word for nucleus or element, we have X, which is the element's name. So let's take an example of radium. Radium, the abbreviation is Ra. So if you had radium-218, 218 is the mass number. That tells you the total number of neutrons plus protons. Another way of doing it is just write out the word. So for example, it could be radium-218. That means the exact same thing as this. And then the atomic number of radium is 88. But you can see you really don't have to put the Z down because the only element with 88 protons is radium. The mass changes depending on what isotope you have. And the reason you can also write it this way where you put the element dash the number, this is before we had all these fancy text formatting tools. And you could just basically type letters in a dash and then a number. So both of these are ways of saying radium-218, and you can even leave the 88 out and just have 218 radium, because 88 and radium really tell you the same thing. Fill in the chart with the numbers of nucleons, protons, neutrons, and electrons for aluminum-27. The mass number, also known as A, is on top, right over here. This specifies the total number of nucleons, in this case 27. The atomic number, Z, is on the bottom, right here. This specifies the number of protons, in this case 13. The number of neutrons, N, is found by subtracting the atomic number from the mass number, or N is A minus Z, 27 minus 13 is 14. Notice how the number of protons and neutrons together equal the number of nucleons. Unless otherwise specified, we can assume the element is neutral so that the number of electrons equals the number of protons, which is 13. Ernest Rutherford estimated the size of the nucleus by using the conservation of energy. He assumed a head-on collision between an alpha particle and a gold nucleus. Remember the gold foil experiment? And that all of the alpha particle's kinetic energy would transform into electric potential energy. The alpha particle would approach the nucleus, and as it's getting closer to the nucleus is repelling it because the nucleus has a positive charge, as does the alpha particle. At a certain point, and this is what he assumed the radius of the nucleus was, the alpha particle would stop momentarily as the 2 forces balanced. The repulsive force from the nucleus between the nucleus and the alpha particle, and the initial kinetic energy of the alpha particle which was shot at the gold nucleus. So at that point you would have the kinetic energy equal to 0 and the electric potential energy would be a maximum, and then the alpha particle would rebound away. So Rutherford calculated that the radius of the gold nucleus would be 3.2 times 10 to the minus 14th meters. Further experiments by many other researchers came up with this equation. The radius of a nucleus with an atomic mass of A is R0 times A raised to the 1/3 power, where R0 is 1.2 times 10 to the minus 15th meters. So nuclei have radii in the range of 10 to the minus 15th meters. So physicists are always looking to name things after other physicists. So when you deal with nuclei, there's a term called the femtometer, which was named in honor of Enrico Fermi. It's also called the Fermi. And it's equal to 10 to the minus 15th meters. And Enrico Fermi is very famous for constructing the first self-sustaining critical nuclear reaction, and he did it in Chicago. Now, just to give you an idea on the size of the nuclei before we compare them here, the term here, it's dependent on the atomic mass to the 1/3 power. All nuclei are pretty much the same, because if you have an object with an atomic mass of 8, 8 to the 1/3 gives 2, so you have a factor of 2 times R0 to come up with its radius. If you have an object with an atomic mass of 216, well, the cube root of 216 is 6, so it's only 3 times larger than a very tiny element. So nuclei tend to be in the same area of femtometers. Now, atoms have radii on the order of 10 to the minus 10th meters, 5 orders of magnitude larger. So you can see how tiny the nucleus really is. However, as small as a nucleus is, and how large the individual protons and neutrons are, the cool thing, again, is the charge on a proton is exactly the same as an electron. And yet the proton is 1,836 times more massive than an electron, yet the charge is the same. Electrons were described by both the Bohr model and the Schrödinger equation as being in well-defined energy levels. When the electrons move between levels, they either absorbed or emitted a photon, depending on whether they move to a higher or lower energy level. These photons can be in the infrared, visible light, ultraviolet, or X-ray areas of the electromagnetic spectrum. The structure depended mostly on the attractive Coulomb force between the nucleus and the electrons, and a slight repulsive force between the electrons. The nucleus also has energy levels, but they're much more complex than the electrons. The reason is you have very strong repulsive, in this case, electromagnetic forces, the Coulomb force, between the protons that are packed within a very small volume. The force acts over an infinite distance, but decreases in magnitude as they get further apart. But the protons never really get too far apart from each other. They're compacted into that femtometer range. Contrasting with that, you have the strong nuclear force, which is giving you an attractive force, not only between the protons and the neutrons, but between protons and neutrons and neutrons. Now this force only acts over a distance of 10 to the minus 15th meters, the size of the nucleus, and actually it increases in strength to a point. So as the two protons get a little further away from each other, the force gets stronger. The strong nuclear force gets stronger. They get attracted more closely. But if they get too far apart, for example, if they get greater than this 10 to the minus 15th meters, there'll be no force. So it's this interplay of the attractive, strong nuclear force and the repulsive electromagnetic force that gives rise to the nuclear energy levels. Summarizing, we have the strong nuclear force, which will oppose the repulsive Coulomb electromagnetic force and will keep the nucleus together. The analysis of these competing forces creates a more complex energy level scheme. However, just like the electron energy levels, the nucleons can move between these energy levels. Nucleons meaning the protons and the neutrons. And when this occurs, very, very high energy photons in the form of gamma rays are emitted or absorbed. This is the most energetic form of electromagnetic radiation. So when electrons change levels, you can get visible light, you can get infrared, you can get X-rays. But X-rays are the most powerful rays that will come from electron transitions. Gamma rays will occur with transitions within a nucleus. One more force in the nucleus, the weak nuclear force. So that's the third fundamental force. We have strong nuclear, electromagnetic, now the weak nuclear force. And that's responsible for the radioactive decay that converts neutrons to protons. And again, that's when you get into the whole notion of quarks, which we're not going to cover here. And the last fundamental force of the four is gravitational, and it is far too small to even be measured. What is the nuclear radius of silver 108? What is the nuclear radius of silver 108? The problem gives us this. That's the mass number, 108, and that typically is the number that follows when you talk about an element. So silver 108, A is equal to 108. R0 in our radius of the nucleus equation was found experimentally to be 1.2 times 10 to the minus 15th meters. So we plug in the constant here, and then here's 108 to the 1/3 power, calculate out our math, and we get 5.71 times 10 to the minus 15th meters. But 10 to the minus 15th meters is a femtometer. So the radius is 5.71 femtometers. Now either one of these answers would have been correct on an exam because they're the same number. Isotopes. Nuclei with the same number of protons are the same element. But when they have different numbers of neutrons, different atomic masses, they are called isotopes. So, same number of protons, different number of neutrons. For many elements, there are a few different isotopes that occur naturally. Isotopes of a single element mostly have the exact same chemical properties because chemical properties depend on the electron structure. And isotopes all have not only the same number of protons, but also the same number of electrons. So they're pretty much the same chemically. There's some difference, but for the most part they act the same chemically. However, they can have quite different nuclear properties. For example, one isotope could decay in 1 microsecond. That's the total amount of time that isotope would live. An isotope of the exact same element, but a different number of neutrons, will never decay. It will stay forever. It will never break down into anything else. But the chemical properties, again, which depend on electrons, will stay the same. Natural abundance is the percentage of an element that occurs as a certain isotope in nature. So if you have a natural abundance of 99% for one particular type of isotope, that means if you found all of the different isotopes of that element on the planet Earth, 99% of them would be that particular isotope. Many isotopes that do not naturally occur, so they're not part of the natural abundance, can be created in the laboratory with nuclear reactions. There's a lot of numbers on this slide, so let's take this one slowly. Atomic mass. We don't talk about kilograms because they're way too tiny for that, and again, physicists somehow take very simple units and make all kinds of different ones to, specifically to work in their field, but to somebody coming in from the outside, it looks horribly confusing. But let's look at this thing. Unified atomic mass units, abbreviated U, and some textbooks you'll see it abbreviated AMU, but we're just going to call it U here. And we're going to say that a neutral carbon atom that has 6 protons and 6 neutrons has a mass of 12.000, etc. atomic mass units. Okay? So, if you were then to calculate the actual mass of the protons and the neutrons, multiply 6 times the mass of the proton, 6 times the mass of the neutron, which is slightly heavier than the proton, you will find that one atomic mass unit, here's a definition right here, is equal to 1.6605 times 10 to the minus 27 kilograms. When we work in nuclear physics, we need a lot of significant figures because, well, one thing, we can measure that well, and also a lot of the effects only come out at the 3rd or 4th decimal place. So that's why you're going to see a lot of numbers to the right of the decimal point. Now, this isn't good enough for us. We want to represent the mass in other types of formats. So we use Einstein's E equals mc squared, and we also have another unit of energy here. Joules is what we were taught first semester in mechanics. We now have a thing called the million electron volts. So 1 MeV is 1.602 times 10 to the minus 13 joules. We take Einstein's equation, divide through by the speed of light squared. See the c squared there? And then I plug in the mass of an atomic mass unit in kilograms. That's this guy right here, comes down to here. And you can see we have another decimal point here. We put a 4, another number to the right of decimal point, times the speed of light squared, divided by a conversion from joules to MeV, and we come up with an atomic mass unit is also defined as 931.5 MeV per c squared. The reason we do that is it helps when we talk about different equations, different ways of expressing nuclear physics. So we have 3 ways to talk about mass at the nuclear level. We have one atomic mass unit is equal to 1.6605 times 10 to the minus 27 kilograms, which equals 931.5 MeV per speed of light squared. Hopefully this slide will make things a little clearer from the previous one. We talked about 3 ways of representing the mass of an object, of these electrons, protons, hydrogen atoms, neutrons. And we're actually calling it rest mass, which is the mass of the object when it's not moving. And the reason we talk about that, when you get into relativity, the mass changes, but we're not going to talk about that in this section. You can see the rest mass of the proton is slightly less than the rest mass of a neutron. So here's kilograms. We're very comfortable using kilograms. We've been doing it all year. In atomic mass units, that's the U here, you can see where a proton is a little larger than one atomic mass unit. The neutron is larger still, okay? And then over here you have the 3rd way of representing mass. So these are just 3 ways of telling you what the mass of these particles are. And you can see how massive the proton, hydrogen atom, and neutron are compared to an electron. An electron is very tiny, 0.511 MeV per c squared. And a good way to remember the mass of an electron, the rest mass of an electron in these units, is on highways now you'll see signs saying dial 511 for highway information. I'm not sure if they copied that off of the rest mass of the electron. Probably not, but it's a good way to remember it. Because the atomic mass unit was defined for carbon-12, remember carbon-12 has 6 protons and 6 neutrons, so we said its atomic mass in atomic mass units is exactly 12. That's the only isotope where the atomic mass is exactly equal to the number of protons plus neutrons. For other elements, their exact measured atomic mass is slightly different from the number of protons plus neutrons.